So welcome to Asynchronous class session number 3. In this session, these are our learning objectives. And so this session is going to have 3 videos. The first video is going to cover these first 3 learning objectives. So the characteristics of the normal distribution, finding a z-score, and determining if a data value is unusual in a normal distribution. The second video is going to cover objective number 4, which involves finding probabilities using the normal distribution. And the last video is going to cover the topic of the central limit theorem, which we often abbreviate as CLT. So let's go ahead and get started with video number 1. Many of you are probably already familiar with the normal distribution or the normal model, but it's the reason you're familiar with it is because it's one of the most widely used models for continuous numerical random variables. And there's going to be lots of examples in our talk today. It's also sometimes called the bell curve because of its shape. And these words are all used interchangeably in the literature. Normal model, normal curve, normal distribution. So you just have to kind of get used to the fact that there's different ways of referring to this model or curve. So here's the normal curve, which again, you've seen many times, and you can see why it's often called the bell-shaped curve because of its shape. It's symmetric, unimodal, meaning it has one hump or one big hill shape in the center, and it's determined by its mean and its standard deviation. So what we mean by determined by the mean and standard deviation is that if you know the mean and standard deviation of a distribution, then you know exactly what the shape is going to look like. And there'll be some pictures of this in slides coming up. So here's some examples of various variables that are normally distributed. So for example, diastolic blood pressure follows a normal distribution. So the mean is somewhere here in the middle, so somewhere in the, I'd say, low 70s. And you can see what the shape looks like. We can see that, values over 105 and under 30 are quite unusual. Similarly, height is normally distributed. Many people are kind of an average height. This looks like the graph for heights of, well, it's hard to tell right now. I think this is probably the heights of males. Excuse me, because the average height is about 69 inches or about 5'9". So definitely this would be the height of males. And there's some unusually, less people are very, very tall, less males are rather on the short side. Now this is what it means when we say that the curve is determined by its mean and standard deviation. So on the left here, we see 2 normal curves, a red one and a blue one. They have the same mean, the same number in the center, but their spreads are different. So the spread is measured by a number, as we've talked about before, called the standard deviation. So the red curve has a smaller standard deviation, meaning it's skinnier, and the blue curve has a wider standard deviation, a larger standard deviation because it's wider. On the right, here we have 2 curves that seem to be spread out in about the same manner. So the standard deviations of these 2 curves are the same. But what is different is where their center is. So this one has different means because the mean is where the curve is centered, but the same standard deviation. Whereas the one on the left have different standard deviations, but the same mean. So their spread is different, but their center is the same. Okay, so that's an introduction to the normal curve. The reason that the normal curve is important is because the area under the normal curve gives us important information about our population. So the area under a normal curve, for example, here's a picture of the heights of females, and the mean is 64 inches, and the standard deviation is 3. So by the way, this is how that's often abbreviated. So N means that it's a normal curve, 64 means this is the mean, and the second number, 3, this is the standard deviation. So the area under this curve corresponds to the percentage of women that are taller than 62 inches. That's the shaded area right here. Another way of thinking about that area is that it also corresponds to the probability that a woman randomly selected is taller than 62 inches. So the area under a curve can be interpreted two ways. One as a percentage of people falling under a certain characteristic, and secondly as a probability that a single person has a certain characteristic. Now, there's something called the empirical rule, which gives us a rough guideline on how to determine if a data value is unusual. So according to the empirical rule, it tells us that if we have a distribution which is normal, about 68% of the data will be within one standard deviation. About 95% of the data will be within two standard deviations, and almost all of the data is going to fall within three standard deviations. So let's take a look at that in a picture. All right, so from here to here, from the mean to one standard deviation, 68% of your population will fall in that region. If you go out farther, two standard deviations, that's going to be 95% of your population. And you can see that by the time you go out three standard deviations on either side of your mean, almost the entire population is under the curve. There's just very few bits out in these top two very tiny tails. So often this is referred to as a statistical norm. So researchers use the word normal to describe behavior. And so sometimes they'll be, for example, studying a link between obesity and sleep duration. And they might state that short sleepers are at a higher risk of obesity compared to, quote, normal sleepers. So what does that mean when researchers say normal sleepers? Well, what they're saying is that since 95% of the population will fall within two standard deviations, falling within two standard deviations of the mean is considered the statistical norm. And anything that's beyond two standard deviations is considered unusual. So the statistical norm is any data that falls within two standard deviations of the mean. And there'll be more examples of this coming up. Now, one way of measuring how close you are to the mean or how many standard deviations you are from the mean is by computing something called a z-score. So literally, the z-score measures how many standard deviations a data value is from the mean. So for example, if your z-score is 1.5, it means that your data value is 1.5 standard deviations above the mean. Z-scores can be negative, so negative z-scores simply mean you're below the mean. So a negative 1.5 z-score means your data value is 1.5 standard deviations below the mean. And this is how your z-score is computed. You take your data value, and you subtract the mean, and you divide it by the standard deviation. Okay? So since 95% of all observations in a normal distribution are within two standard deviations of the mean, any z-score above 2 or below negative 2 are considered potentially unusual. So here's an example. Heights of women in the US are normally distributed with a mean of 64 inches and a standard deviation of 3 inches. So let's just draw a little picture of that. I'm big on drawing pictures. You don't have to draw a picture, but for me, I think it's helpful. Okay, so here's our mean at 64 inches. And the standard deviation is 3 inches. So if we go out 2 standard deviations to the right, this number would be here, would be 64 plus 3 plus 3, or in other words, 70. If we go out 2 standard deviations to the left, this number here would be 64 minus 3, or in other words, 58. So heights between 58 and 70 inches would be considered statistically normal. Any height greater than 70 inches would be considered unusually tall, and similarly, any height less than 58 inches would be considered unusually short.